welcome back to Talks for this afternoon. I have the absolute pleasure of introducing Caleb Brown, who will be talking to us all about how archives can be very vulnerable.
Thanks. All right. I'm glad you could all join me after lunch. I hope you can not fall asleep. So, as you've already heard, I'm Caleb. I work at Google as a software engineer, and I work on open source security. I also do a bit of work on deps.dev, and some of my teammates will actually be talking next. I'm also a maintainer on something called the OpenSSF Malicious Packages project, which means I get to see lots of reports about malware all the time. And so my background in Python and my work in security got me wondering a while back. How secure are the technologies our ecosystems are built on? I'm talking about the fundamental technologies, the nuts and bolts. For me, my interest has been focused on packaging, so source lists, wheels, that sort of thing. So having spent a fair amount of time poking around Python packaging, I was intrigued when I read a report earlier this year that used tar files and symlinks to compromise a system. After reading that report, I immediately wondered if Python's tar files were vulnerable to the same symlink-based attacks in tar files. And long story short, I found 3 vulnerabilities in the tar file library in Python. And these were fixed earlier this year in this version of Python, along with 2 other tar file CVEs as well. But today, I really want to focus on this one here. Particularly because this vulnerability is the most serious. This vulnerability allows a malicious tar file to write anywhere on the file system, well, at least anywhere with privileges to do that. And while I explain how this particular vulnerability works, I would like to discuss, I guess, some general security concepts and ideas I was reminded of while I was discovering this vulnerability and the others. So to get started, we need to go over some background just so we're all on the same page. I'm sure most of you are familiar with tar files, but I'll cover it briefly. tar stands for tape archive. It's really old. And its original intent was for backing up your system to a tape file. And so it's kind of intended for this sequential operation. And it doesn't do compression by itself. It's just usually you add some compression on later. So you might see a .tar file followed by a .gz or .bz2. That's the compression added afterwards. And it can store stupid things as well as normal stuff like you expect, like files and directories, but it also stores device nodes and FIFO. So that's tar files. The other thing we should all be on the same page about is symlinks. If you're not from a Unix background, these are kind of like shortcuts. So a symbolic link is essentially a file. It stores a path to some other place on the file system, and we call this the target. And for a lot of file system operations, it just behaves like the target. So if the target is a file, you can open it, you can read to it, you can write to it. If it's a directory, you can list the contents. So that's symlinks. And the last thing we need to introduce are path traversal vulnerabilities. So in a path traversal vulnerability, you've got a file system. There is stuff in your file system you really don't want people to touch. There's stuff there that's where you expect things to happen, that's here. So when you are doing operations, you kind of want everything to stay in that circle. But a path traversal vulnerability is when an attacker can manipulate the input, usually a file name, in such a way that it can get out of that circle and access something else in the file system it wasn't meant to do. Now, if you're from a web background, you might be familiar with this sort of pattern, where you have a query parameter, and someone's just added a whole bunch of dots. This is like the most simplest thing. There are a lot more complex ways of injecting the path traversal. But then you can see that it just gets passed straight into open. And if this Django snippet was run, it would dump your entire password file into the web response, assuming you had permission to read it. Archive vulnerabilities are kind of similar. There's just a file name and a bunch of content, and it's user supplied. And so if you had a tar file with a file name like that, it would extract and It'd output some authorized keys into your SSH directory and give the attacker access to your host, potentially the root account. Now, archive vulnerabilities that are path traversal vulnerabilities has a term that's commonly used called zip slip. This was coined in 2018 by Sneak. It's sometimes called tar slip for tar files, but they're basically the same type of vulnerability. But for Python and the tar file library, its history of path traversal vulnerabilities goes back a lot further. So in 2007, a CVE, a vulnerability report, was created about path traversal in the Python tar file library. So not much happened for a while. And then in 2023, with PEP 703, it introduced the concept of filters to tar file so that you could make the extraction safer. And it provides two filters that we care about. The first is the tar filter. And its job is basically to behave like the command line, the tool, the tar tool. And so the main thing it does is stop you using absolute paths, and it tries to avoid path traversal for writing. So if you give it a destination, all the writes should stay in that location. The other filter is the data filter, and it does everything the tar filter does, but it's stricter. It also tries to avoid having links inside a destination that point somewhere else. And it does other things like only lets you extract like files, symlinks, but not device nodes. And it does sensible things like setting permissions and stuff on directories. And this is going to be the default next month when the next version of Python is released. Along with this PEP, they also added some more changes to the API so you could use them. You can go into tar file and you can add your filters. You can even add them if you're using it from the command line. So these changes got me thinking about, these filter changes got me thinking about security retrofits. And the first big point here is that retrofitting security is hard. It's hard because usually you're doing it because you're forced to. It's in reaction to a vulnerability or a compromise. It's also hard because usually you're adding security to a place where there's existing code and there's existing technical debt, and you've got to manage that. And after you've added your security fix or you've hardened the security, the complexity and the technical debt is usually a bit higher than it was before. And then after all that, you've got to deal with, like, maybe you've had to change something in a way where you need to migrate systems or get users to change to a new process. Retrofitting security is hard. And when you do it, please avoid shortcuts, because you are going to do it. But avoid shortcuts. Fast fixes have their place. If you have a critical vulnerability, you're leaking private user data, do what you need to do to get that closed. But otherwise, it's really important to approach security hardening carefully. What are the trade-offs with your solution? What are you gaining? What are you losing? It's good to avoid unintentional consequences. It's very easy for an intended security fix to actually introduce new vulnerabilities as well. And you also want to take your time and be careful because you want to limit complexity. Complexity is the enemy of security. And in the long term, if you take shortcuts, it only makes the challenges of retrofitting security harder. But retrofitting security well is worth the effort. If we look at the tar file filters, the secure default is almost here. It lands next month. And this secure default, for anybody who's using Python 3.14, is the default. It means that they're all protected by this change. Also, the change is well considered. It's only a small API change, and it's optional. If you're using it to opt out. And the last thing, and probably most importantly, is that it's a centralized implementation that is strong and well tested. If we didn't have this, you'd be forcing developers to all go and do it their own way, which risks them doing it wrong and for everyone having different vulnerabilities all over the place. But I'm getting ahead of myself. We still haven't got to our vulnerability yet, and I'm sure that's why you're here. So let's go back to these filters. The vulnerability that I'm interested in is focused on breaking this. We want to be able to write files anywhere we want on the file system. So the vulnerability I've found does allow this. Let's jump into tar file implementation in Python. I promise you it's not going to be like super detailed. You'll be able to hopefully follow along. So first of all, here is the extract all function in the tar file module. I've simplified it. I've got rid of code you don't need to worry about. It ensures, the first thing it does is it ensures that the filter function is actually a function. So you can pass in a string or a callable or none, and it will make sure that's something you can call. And then it goes through each member in the tar file, one by one, in the order that they appear in the file. And then for each of the members, it will call this function get extract tar info, and that basically just applies the filter to each member. And then after that, it extracts the single member. So what are the filters doing when it calls that? This is a simplified version of the filter. And this is specifically like the top part of the function. And this bit of code is only about making sure that the file that we're writing, or the directory we're creating, is inside the destination path. And you see there it's got this real path call, which kind of gets rid of traversal and links and stuff, and there's another one, and there's this check to make sure that they both start with the destination prefix. And you might be wondering, this code looks pretty normal. Can't see much wrong with it. And when I was looking through this code, I passed over this many times, and I thought it was perfectly secure as well. But I started wondering, RealPath is doing a lot of heavy lifting here. What does RealPath actually do under the hood? Maybe we can find a bug and bypass these checks. So let's jump into RealPath. We're going down the layers here into more and more detail. So RealPath has a basic process where, firstly, if the path is relative, it makes it absolute by sticking the current working directory on the front. Then it goes through each of the path element. It splits on the slash and then slowly builds up from left to right the path, checking each one as it goes, or processing each one as it goes. So A, then /B, then /C, all the way. So as it does that, it does this very basic set of things. Firstly, if it's a dot or a dot dot, it deals with that. If it's a dot, it'll get rid of it. If it's a dot dot, which is a parent traversal, it gets rid of the dot dot and the one just to its left. If it isn't one of those, it'll call lstat. Lstat is an operating, like a wrapper around a system call that returns data about the path. And it's specifically used to check if it's a symlink. And if it is a symlink, then it calls readlink and replaces the element in the path with the contents of that link. And it does that over and over again until it's done. So this all looks pretty normal. But then we start to see interesting things. Oh, this is not working. Oh, now you decide to. Sorry, it's giving me like USB warnings. So we look at the error handling. And the first thing I noticed was that the default for RealPath is to be strict equals false. So errors are ignored by default, which means that if the lstat call that checks if it's a link fails, and it could fail for a bunch of reasons, then all of the remaining path elements that it hasn't processed, they essentially get stuck onto the bits that it has processed. Let's exploit this. I think we can do this. All right, let's introduce our favorite thing of the day, which is pathmax. We're now getting even lower into the operating system. Pathmax is a constant, and it's a constant that applies to operating system calls. So this is when you're calling into the kernel. There's this limit that says how many bytes of a path you're allowed to pass to it. This is important to remember. It's not a file system limit. You can make as deep a directory structure as you want, I think, as long as you don't run out of inodes or disk space. And so its main job is to stop you breaking the operating system. And here are the amounts that each operating system has as its limits. We're not going to use that limit because that's kind of big to fit on a slide. So we're going to just assume we have a path max of about 30 because that's what my drawings kind of worked out to be. So assume we've got a buffer here where we're building our path. We'll just stick the destination at the front. That's going to be there. And then let's do something funny. We're going to add a bunch of directories, one by one. And this is important later when we try and traverse out. And then, at the end, let's add a symlink that exceeds the length of path max. And this link is just something that takes us all the way back to the top where destination is. So if we pass the green part and the red part into lstat, this is what happens. The first one passes happily, it returns the information about that directory, but the second one doesn't. It throws an error. And by default, RealPath swallows that error. So what happens, we're kind of stepping out now. We'll go back to have a look at RealPath and have a look at what it does. So if you pass that long link with the symlink at the end that exceeds pathmax into RealPath, what it returns is the unexpanded symlink. But what it should have returned is either an error or /dest, which is kind of a problem. So this is a problem. Any path element that is overlapping or after pathmax never gets expanded. So this behavior of RealPath has me thinking about abstractions. Abstractions are really good. They're about, in computing, they're about providing access to something and about hiding details and complexity so you don't have to deal with all the minutiae. And in the end, an abstraction allows you to think at a more high level about what you're doing. Abstraction is powerful. Computing is built on layers and layers of abstraction. It's awesome. Like, who has written machine code or assembly recently? Oh, is it 2? What about anyone like writing a raw Ethernet frame to a network interface card? No. Does anyone know what those terms mean? Yeah, there's a few of you. Okay, good. This is why abstractions are awesome. You don't have to think about all that stuff. Programming languages are an abstraction. Operating systems are an abstraction. Even the tar file library is an abstraction over a collection of bytes in a file. But abstractions do have a weakness. They can make security harder. And they do this in a variety of ways, and these are the 4 that I came up with. They make the problem simpler than it should be. And this is often the case with I/O. They can bury critical security flaws that you should be made aware of but don't know. They can have default behaviors that aren't secure. And the last one is harder to explain. They are leaky. There are side channels. Spectre and Meltdown or Rowhammer are examples of this type of abstraction problem. So if we look at RealPath, it has a couple of these. The first is obviously the insecure default. Strict equals false is an insecure default. It ignores any error that is thrown inside it. But we can't simply just change the default to true because of oversimplification. If we did that, it's all or nothing. You don't get the nuanced behavior. It forces that onto the user of that function, which is not great. The name too long error is not the same as it doesn't exist. So different errors need different responses. And in fact, one of the main fixes to this vulnerability was introducing a new behavior for strict in RealPath called allow missing. So all errors are thrown in this case, except if the lstat call fails with a missing, file not found. You're seeing my RAM scripts. So abstraction presents a challenge. On one hand, it hides a bunch of details, which is both its strength and weakness. It allows higher level thinking. It lets us build bigger, more capable systems, but it also hides important security-related details and issues. So when building secure systems, it's important to consider our abstractions. All right, oh man, I'm running out of time. I thought I had more. So we're back here with our leaky abstraction, RealPath. We already saw this. Let's turn it into an exploit. here we go. This is our tar file. The first thing we do is we create that directory. The next thing we do is we have to create a symlink to the bottom of that directory. And then we use that symlink we create to create the really long link. And we need this actually because you know how that path is too long? We can't just create the symlink, or the creation of the symlink will return the same error. So we use the symlink to kind of trick it into creating the thing that exceeds the length. And then we have this escape symlink, and this is really just to make things nice. And then we have our payload at the end, which is to overwrite the authorized keys. And what happens is the input, so this is the file at the bottom, and this is kind of reversing those symlinks. The escape is actually, this is what it means. So we have this really long path, and that really long link, remember, is this directory traversal, which takes us all the way down to the root. But because of the bug, because of this pathmax bug, what happens instead is that real path returns this, but in reality, it's this. And because real path returns this, target path in our filter is set to the output of real path, and this check in the common path at the end of the filter passes, and we now can point target path anywhere we want. We can write anywhere in the file system we have permissions to. Our arbitrary write is achieved. So you might be thinking, like, why do we even have symlinks in tar files? Well, this got me also thinking about symlinks and incentives. So you have, I'm going to simplify the world down to just a library user and a library maintainer. And statistically, the maintainer is just one person in their spare time. And the user is kind of interested in these things. They want to ship features. They don't want to break their stuff. They want to keep it working. They want their boss to be happy. But a maintainer, our statistical maintainer, is more interested in these sorts of things. The maintainer has a day job. They have a personal life. They might have a family. They might have health problems. They might be caring for elderly people. Who knows? They just want to resolve their issues quickly and keep their users happy. And at the end of the day, the user only cares about a limited feature set, but the maintainer, in wanting to keep their users happy, is interested in building a general purpose library. So symlinks are in tar file because it's a general purpose library. So what can we take away with that from this? You need to be wary of incentives. For a user, be wary of large feature sets. Disable things you don't need. Be careful of things you're opted into without being able to control. For a maintainer, think about building for default secure and making stuff that isn't core optional. And make it optional, but also make it opt-in. And I really like Django's approach to this in some ways, where you can pick and choose the bits that you want. So beware of different incentives. All right, I've got a minute or two left. I think we've got time for a demo. Hopefully this all works. I had multiple demos, but I'll do this one first. So this is we've got a file system here. We have two directories. This is where we're going to extract the file into destination. Do not touch is the thing we don't want to touch. We have our very important document in here. If I open it, it says on my screen, not yours. Let me drag this over. It says hello world. Okay, this is great. But in our demo directory here, we have this tar file, poc.tar. I'm gonna list the contents of this tar file. It's very long. And because this is like a Mac-based operating system, we need really long paths. So there's a whole bunch of these directories and symlinks and stuff going on. But we can see at the bottom some of the stuff we're going to do. Those flag links are, one of them creates a hard link, which I won't get into, and the another changes its contents. So what I'm going to do is I will try and find my copy and paste command on the other screen, because I don't trust myself. Oh, just to prove that I'm using a vulnerable version. We've got this. I had to use UV because you're going to... All right, this is a vulnerable version, so it's not one of the ones that's fixed. I'm using UV because it lets me pick the Python I want to use. All right, now we're going to... Oh, wait, I'm not in the destination file. We'll go into the destination. And now I run my POC. And the first thing you'll notice is not a lot happened there, but if you look in our do not touch directory, a couple of things happened. There's a new file there, and the important file has, let's have a look at it. Oh, it's opening on my screen. Let's drag it across. Oh, this one now says that. And this one created a new file as well. So there we go. It works, which is good. You can't see the cooler demo where I created a quick website using Gemini, and you can upload tasks to it, and it's fun. All right, let's just jump back into the presentation. So wrapping up quickly, while I've still got a minute, I hope you've enjoyed me talking about breaking things. Finding vulnerabilities is a roller coaster ride, but I also hope you take away some new ideas about security and retrofits, abstraction, and incentives. This is important because attacks are growing, particularly in open source. I don't know if you've heard about phishing and NPM. And regulations are increasing as well. And new laws like the Australian Cyber Security Act, these are mouthfuls, and the EU Cyber Resilience Act, these are acts that change the landscape for software engineers in terms of what we are required to be doing. So tackling cybersecurity is more important now than ever. And finally, upgrade your Python. You can check download stats, and like 42% of people downloading, clients downloading from Pipey are like from vulnerable versions. And if you're interested in metrics like this, stay for the next talk, because they'll talk more about that. Yeah, that's me.
Thank you, Caleb, for the wonderful talk. I do have a nice speaker gift for you.
Thank you very much.
Our PyCon AU 2025 mug. We might have time for one question, if anyone has a question.
If you want, if there's a question, I'll happily answer it. But I also have like more demos. So if you want to see more demo,
Might have time for another demo.
But anyway, question's probably better.
Sorry, have there been vulnerabilities found in Python's own, legacy type file formats like pickle or shelf? And what would you suggest in terms of going about opening a pickle or a shelf from 10 years ago or 20 years ago?
What sort of file format? Sorry,
Pickle or shelf?
Pickle or shelf? I'm not familiar with shelf. Pickle does have its well-known problems, particularly in the AI space and sharing models and that sort of thing. So pickles are a well-understood problem, and I think there are mitigations to deal with that. I'm unfamiliar with the shelf example, but I'm sure there are vulnerabilities if they're old and unused.
That's all the time we have for questions. Please join me in again thanking Caleb for his talk.
Thanks.